All right, welcome back again, everybody. Today we're going to be doing section 14.4, which is all about linearizations and tangent planes. So let me pull up the slides and we'll get started. All right. Okay, so let's just look at the overview to start. So one thing I'll say is this section is a little bit long, but really it's a little bit long because it's a little bit technical. So what I'm hoping is that most of you kind of recall at least a little bit from linear approximations from back in Calc 1. I know that it's a section that I tend to emphasize quite a bit when I teach Calc 1 because it's kind of like it's like one of the fundamental core concepts that you learn in Calculus 1, this notion of approximating a curve with a line. That's like a big idea in calculus, right? That you can zoom in on a differentiable curve at a point and it will look like a line when you zoom in close enough. That's kind of the idea. Now we're gonna generalize that. So we're gonna start with a motivating idea. Then we'll talk about tangent planes, because now we're working in higher dimensions. We'll talk about linear approximations and what they are and how to define them. Then we're going to get what's called the characterization of a differentiable function. And this is where some of the technical details come in a big way, in like an important way. Like you need the rigor and you need the technical details to make the thing behave the way you want it to behave. Um, then we'll come up with a definition of a differentiable function. Then we'll pivot and talk about differentials, which is another way of looking at linear approximations. And then we'll talk about extensions to functions of several variables, because again, all this stuff extends to higher dimensions and multiple variables. All right, so here's the motivation. Some of the key core concepts explored in Calc 1 are differentiability, tangent lines, and linear approximations. It's kind of like why you study calculus, Calc 1 at least. So the idea is this, I briefly said it a moment ago, but if you zoom in on a point on a differentiable function of a single variable, the curve begins to appear like a line. And so what you can do is you can use that line to approximate the curve at that point. At at that point. So that's one of the reasons we care about the derivative. It's one of the reasons we do calculus at all. Because if you've got a differentiable function, then what it means is you could just use a line instead of that function, and the line will be pretty close to your function, but you have to admit a little bit of error. So that's why it's an approximation, not an equality. And the line that approximates the curve at that point is what we called the tangent line at that point. And it is quite literally the linear approximation of the function at that point. In this section, we're going to extend that idea to multivariable functions. And how do we do that? Well, we do that with planes. So if you remember back from section, oh geez, I don't remember anymore, 12.5 perhaps, we talked about how a linear function in two variables, or actually I should say this, a linear function of three variables is a plane, right? It's a tangent, or it's a plane instead of just a line. And then as you go up in dimensions or go up in the number of variables, you get hyperplanes. So here's the setup. Let S be a surface given by some two variable function, and we're going to insist that F has continuous partial derivatives. So we're going to insist upon that the partial derivatives are continuous, F sub X, F sub Y. We're going to let P be a point on the surface. Here it is in the picture. We're going to let C1 and C2 be the curves of intersection of S and the planes that pass through that point. So C1 is this, and C2 is this right here. Same idea we saw in the previous section where you slice the surface with a plane at that point, and you get a curve. You get a curve of intersection. We're going to let T1 and T2 be the tangent lines to the curves at that point. Then what we say is that the tangent plane to the surface at P is the plane that contains both of these tangent lines. All right? So I want you to just look at this and think about it and just ponder it for a minute. Stare at that picture, reread this once or twice, and just get the idea in your head before we proceed. Okay. All right, so the tangent plane is the plane that best approximates the surface S at the point P. So this is very much like a tangent line for a single variable function. This plane that you see is the plane that best approximates the surface at that point. The other thing is any other tangent line will lie in this plane. So this tangent plane actually contains all possible tangent lines as well. So now the big question is this. What's the equation of that plane? I want to find that plane. I want to know what the equation is, what the formula is for a tangent plane at a point. That's huge. I definitely want that. So what we're going to do is we're going to start from scratch. We're going to use our general definition of a plane. So any plane that passes through that point has to have this form. That's what we learned back in 12.5. We're going to do a little bit of relabeling just to clean things up. If we divide both sides by c, and then we're going to call negative a over c a and negative b over c b, then we can rewrite this equation like so, just like this. Yep, yep. Okay, so now it's starting to look a little more like the other form of a plane that we had from back in 12.5. So if we substitute y equals y naught, we get this. And this is just the point slope form of the equation of the tangent line T1. This is one of the reasons why I like to emphasize point slope form back in Calc 1 and in Calc 2. Not everything needs to be written in slope intercept form. Point slope is often more helpful for calculus because all of our analysis is localized at a point, and we want to start at a point and go somewhere from that point. So here, this is just the equation of the tangent line T1. But if you remember from the previous section, we found the slope of that tangent line. That's the partial derivative in the x direction, right? So the slope of this tangent line here is f sub x at that point. So we must have that this coefficient a is f sub x of x naught, y naught. And then similarly, if you do the same thing, plug in x equals x naught to our original equation on the previous slide, you'll find that b has to be f sub y. So we get this theorem, which is very cute. So suppose f has continuous partial derivatives, then an equation of the tangent line to the surface at that point P is given by this formula right here. And this is a formula that you should memorize. This is a really important one. And again, it's just so natural, right? It very naturally makes sense. That's the slope of the tangent line in the x direction. That's the slope of the tangent line in the y direction. Those are basically the direction numbers, right? It's like the direction numbers that tell you like where to go in some sense. So this is the equation of the plane. That is the tangent plane. Right. Again, notice the similarity to the point slope form of a line. It's literally a natural generalization of the point slope form. In fact, if you remember from Calc 1, if you're given a differentiable function, you found that the slope of the tangent line at a point is f prime of x naught, right? That was like the big deal, right? Well, the actual tangent line, the tangent line approximation has this form. So just take a moment to like ponder this and just relish the fact that this is getting generalized to this. And it just makes so much sense, right? When you're dealing with a single variable, you don't need to differentiate, you don't need to distinguish between which direction you're taking a derivative, right? There's only one direction. That's why you just say prime. It's the only possible direction, right? But when you have multiple dimensions, even just like two, you have to start to specify which way you're taking the derivative. That's why we get this. But again, it makes sense. This way in the x direction, this way in the y direction, and then you've got your tangent plane. So this is an equation of the tangent plane. All right, now let's try this one. And this is one that I actually want you to try on your own. Oops, let me do this. You try this one on your own, because I think you have all the tools to do it. It shouldn't be too bad. So find the tangent plane, find the equation of the tangent plane to this elliptic paraboloid at this point. All right? So ponder it for a minute. What do you think you should find first? Okay, now say that out loud to yourself. What do you want to try to find first? All right, now write it down. So work it out, find what you need to find, and use that equation that we just saw in the previous theorem. All right, here we go. Let's work it out together. So If we're finding a tangent plane, we got to find some derivatives. We need the derivative in the x direction. We need the derivative in the y direction. We need to evaluate those derivatives at that point. And once we have those slopes in those directions, we should be good. Let's see. Here's the partial with respect to x. Makes sense. Here's the partial with respect to y. Makes sense. Evaluate at 1, 1. Evaluate at 1, 1. Now we have those two numbers and we're basically done. This is the point at which we computed those tangent or those slopes, those derivatives. So now we just use the formula from, well, really the formula for a plane, plug in the point, plug in our partials, and this is the equation of the tangent plane at that point. Boom. Super fun. If you wanted to write it in this form, you can. This is basically standard form, or really, sorry, really this is equivalent to the y equals mx plus b form, right? It's almost like if you know, like if this wasn't here for a minute, it would look kind of like mx plus b. So now it's more like m xy plus b. So it's natural generalization. Okay, now let's get a picture of this. So this is actually a picture of the paraboloid that we just found the tangent plane to at that point. So let me zoom in on these pictures for a minute. Here, the surface is the paraboloid, and this plane down here is the approximating tangent plane, right at the point 1, 1, 3. And the big idea about a tangent plane and the big idea about a linear approximation is that as we zoom in on the surface at that given point, the surface should start to resemble a plane, like a flat surface. So if we zoom in a little bit, right, like here, what is it? Yeah. So notice the indices here. -4 to 4, -4 to 4, -2 to 2, -2 to 2. So you see as we zoom in, it starts to look a lot like the plane itself. Here's just between 0 and 2, right in the middle is that point. And the more we zoom in, the more our surface just looks like a plane, looks like a flat piece of paper. Here's what the contour maps look like. So let me zoom out a little bit. So here's what our surface looks like here, right? And then if we zoom in more, these are what the contour lines look like. If we zoom in more, the contour lines start to look like straight lines, which makes sense, right? Because it's it's starting to look like a plane the more we zoom in. And you remember that the contour map for a plane is just a bunch of parallel lines. So that's like the intuitive idea here. That's what's going on here, right? So now this leads us to be able to define what a linear approximation of a function at a point is, and that's this definition. So the first order approximation, or the linearization, is given by this definition, which I'll say in just a moment here. I'm going to address this. So this is called a first order approximation because, as you saw in Calc 2, you don't just need to use linear approximations. You can actually compute full-on polynomial approximations. And that's what you do at the end of Calculus 2, right? When you learn about sequences and series, and you compute Taylor polynomials, and you talk about Taylor series and Maclaurin series, those things literally are giving you first, second, third, fourth, nth order approximations of a function. Right now we're talking about first order approximations, just linear approximations, not quadratic, not cubic, not polynomial, just lines, planes. So here we go. We're going to let f be a function of two variables that has continuous partial derivatives. We still need that at the point a comma b. Then the linear function L sub f of x comma y is the function whose graph is the tangent plane at that point, and we call it the linear or first order or tangent plane approximation of f at a comma b. So that is literally what that plane is, and its equation is given by this. So this is actually putting it in kind of a, well, the same form that you saw back in Calc 1. So the linearization is given by this. You find the value of the function at that point. Here is the partial with respect to x times x minus a, partial with respect to y times y minus b. And so this is the equation of the plane that approximates the surface the best at that point. Now, moreover, yeah, this is the big idea. F of x comma y is about L sub f of x comma y. As long as your point is near a comma b. I think I say this here. Yeah, I'll go to this slide. The tangent plane to a surface is a linear approximation of the surface. And the moral of the story is, do you really want to have to work with a complicated function, or would you rather just work with a plane and then admit a tiny bit of error, a tiny bit of error? If all of your analysis is localized to a point, I mean, you don't have to move very far away from the point, it might save you a lot of computing time or a lot of headaches or just a lot of time in general to just use a tangent plane instead. That's the moral of this idea. So in example one, we actually found the tangent plane to this surface right here. And so that means we can write the linearization of that surface at that point like so. That was what we found in example one there. So as long as we are very near the point 1 comma 1, this function here will give a pretty good approximation of this value, f of x comma y. It'll be accurate to some decimal place, for example. So you might ask yourself, well, if I need it to be accurate to 3 decimal places, what's the farthest away I could go from the point? Those are relevant questions. Okay, now there is a caveat here. So this is where things are going to get a little bit technical, maybe a lot bit technical. The caveat is this: we've only defined tangent planes to surfaces where f has continuous partial derivatives. So if you remember that, that was in the definitions even. So it turns out that without this condition, the function may behave badly, even if the partial derivatives exist, even if the partial derivatives are equal. And the problem is your tangent plane may not be well defined. So this one is a little bit, how do I say, it's a little bit more subtle because we're going to see in the following example, you could have a point where the partial derivatives exist. The partial derivatives are equal, but you can't define a tangent plane well, meaning that there are infinitely many choices for a tangent plane, which we'll see in a moment. So consider the following example. We are going to show that the following function has partial derivatives that exist at the origin and that they are equal at the origin, but that those partial derivatives are not continuous. And then we're going to see that the linear approximation that these things would give is not accurate. Yeah, so we're going to see a failure, an example of failure here. So here's the function, x comma y over x squared plus y squared, as long as you're not at the origin, and then 0 if you are at the origin, right? So here we go. We're going to have to use the definition of derivative here. So be careful with this. I made this mistake when I was working the example out myself. Remember that we're trying to find the partial derivatives at the origin. So we can't simply differentiate this because that's not how the function is defined at the origin. And we can't differentiate this because that's just the value of the function at the origin. So we do have to go to the actual definition of a partial derivative, all the way back to the difference quotient. This is why we have these definitions. So let's compute it. By definition, the partial derivative in the x direction at 0, 0 is given by the limit of this difference quotient. The increment is hitting the x component or the x coordinate. Here's what we get when I evaluate my function at 0, comma h, comma, actually, wait. Sorry, this should say 0, typo. 0, oops, not that, come back. 0, I'll fix that later. Yeah, okay, so now this is what you get, and you'll find that you get 0. Well, since the limit is occurring away, we're going to get 0. We're going to get 0 here. So this is 0 before we take the limit, and so we actually end up getting that the limit is 0. Do the same thing in the y direction. So use the definition of the partial derivative in the y direction, plug in those values there, and you'll find you get 0 again. So check this out. The partial derivatives both exist, and they are both equal. So there we go. They exist, and they're equal. Next, we have to show that they are not continuous, right? Is that what yeah. Now we're going to show that they are not continuous. So if you remember the definition of continuity, we should be able to approach the point from any direction, right? And see if that limit exists. Well, because we're going to be approaching, we are going to have to actually compute the partial derivatives away from 0. That's what I'm doing here. So away from 0, the partial with respect to x is this. And what I used here was just the quotient rule, good old quotient rule. That's why you're seeing this minus this over this squared. Simplify, you get this. Do the same thing with respect to y. This minus this over this squared. Simplify, you get this. So that's what the partial derivatives are away from 0. Now what we're going to do is we're going to take the limit of this thing as we approach 0 and see what we get. We'll do this one. So the limit as x comma y approaches 0 of our partial derivative is this. And now if you remember from, geez, what section was it? 14.2? I think it was 14.2. This is where polar coordinates can really come in handy. So we convert everything to polar coordinates, change the limit to one where the radius is going to 0, do some algebraic massage here, and we get this. And what you'll notice is that you end up with 3 r's up here, 4 r's down here. So when you simplify, you're left with an r in the denominator. But as r goes to 0, this is going to go to infinity, which is not 0. Like this goes to infinity, so it's not continuous there, right? Same thing if you try to do it in the y direction. So I leave that as an exercise. You can do that on your own if you would like. Do a similar computation, and you'll find that you actually get that you go to infinity as as you approach 0, 0, this partial derivative. So that means that the partial derivatives are not continuous. Yeah, that's right. Right. They're not continuous there, but they exist and they're equal. What's going on? All right, now check this out. So the partial continuous derivatives exist, they're equal, but they're not continuous. That's the main idea. So using the formula for the tangent line approximation, we should have this. Like if the tangent plane actually was a good approximation, check out what we get. F of 0, comma 0 is the function evaluated at 0, partial evaluated at 0, x minus 0, partial evaluated at 0, 0, y minus 0. Everything is zeros all the way down, right? So 0, zeros, everything's 0. So this is telling us that the linearization is just 0. Okay. So the tangent plane approximation has the formula 0. Now check this out. Any value on the line y equals x away from the origin will actually have the value 1/2. So even if you are, infinitely close to the origin, the output of your function is going to be 1/2. But we just found that the linearization should be 0. But 1/2, relatively speaking, is nowhere even close to 0. So that means that our linear approximation is not valid. So there's something missing here. There's something that's causing a failure here. And that failure is actually, it is the fact that they're not continuous. That's basically it. Actually, I wonder, the partial derivatives are not continuous. I wonder, do I have? I don't. Darn, I wish. Do I want to try to throw it up here real quick? I know there's a picture in the book for it. Give me a second here. Let me ponder this for just a moment. You know what? Hold on a second. I want to bring up this image in Mathematica so we can take a look at it. Hold on one second. All right, I'm back. So I quickly made this image on Mathematica. Let's take a look. All right, so here is what it looks like. Here's the function. Here is what the surface looks like, and what's happening at 0, comma 0. All right. Okay, so what I want you to think about here, there's x, there's y, although I kind of want to turn it this way so it's kind of matching what we would expect. All right, so the first thing I want to point out is this. Remember that the partial derivatives with respect to x and y are like the slopes of the tangent lines in those directions, right? So if you look at the surface and you think about what happens as you approach the origin in the x direction, I don't know if you can kind of see it right here. What's happening is the surface starts to get very, very vertical, right? The surface starts to get very vertical. And so what happens is your tangent plane is starting to get it's starting to get perpendicular, right? Or just straight up and down. That's what's happening if you think about just in the x direction. Same thing with the y direction. So if you look close to the origin, what's starting to happen to the surface is it's getting very, very vertical. And that's why everything is failing here. That's why the partial derivatives are going to infinity, because the slopes are going to infinity, right? And then if you look at the surface itself, literally like any point on the line y equals x is equal to 1/2. It's like a constant, right? It's literally a constant. Not even just like, but is a constant. So what's happening here is the failure is the partial derivatives are not continuous at the origin. And what that's telling us is without that condition, we can't well define a tangent plane. There gets to be too many issues at that point. So in order to keep differentiability and linearization and the notion of a tangent plane all working together, we needed that extra condition of the partial derivatives being continuous. And so this kind of motivates why we need a little bit more rigor. I know, again, like I use the word intuition all the time. If you've taken me before, I'm all about intuition and making sense of these things. But this is exactly why intuition is great as a guide, but it's not a proof. And you can't wholly rely on intuition. This is why you need the rigor of mathematics and you need the rigor of analysis and you need the rigor of things like the epsilon delta definition of a limit. And as we're going to see right now, a general characterization of differentiability. So use your intuition as a guide because it oftentimes is correct. But when you start to get down into the weeds, you're going to have to bring in the rigor, right? You're going to have to bring in the rigor. You can't avoid it all. All right, so let's go back to the slides and we'll see exactly how we're going to address this issue. Okay, so, oops, there you go. So yeah, example 2 illustrates that the notion of differentiability and linearizability cannot be defined through the existence and equality of partial derivatives alone. They're not like, yeah, you can't describe them through that alone. You need more. Also, if you recall from Calc 1, even if, I'm sorry, if a function is differentiable at a point, then it has to be continuous at that point, right? That was one of the big results back in Calc 1. Differentiability implies continuity, right? But here with this function, the function that we just looked at, xy over x squared plus y squared, that function is not continuous at 0. You can check it out. You can take a look. It will not be continuous at 0. I leave that as an exercise. You try that on your own. So what we really need is we need a more rigorous and more generalized characterization of differentiability that extends to functions of multiple variables and assures this continuity condition. Right, so now we need to flash back. We need to go back to calculus 1. Um, let me say this. Do I say it here? I forget where. Okay, I will say this. Technically, this characterization of differentiability is introduced in section 2.5 on the chain rule. So if your professor was particularly rigorous, they may have basically introduced this characterization of differentiability in order to prove the chain rule back in Calc 1. So if you look in section 2.5, the very end of that section is a proof of the chain rule. And in order to do that proof, they introduce this definition of differentiability. Coincidentally enough, we are also going to use that definition of differentiability when we prove the chain rule in the next section. That's one of the reasons I like to introduce it here. Speaking personally, I tend not to introduce this in Calculus 1 because there's already so much stuff going on that throwing this into the mix also, or at least this characterization of differentiability just really throws people off. So I like to save it until right now, and we're going to learn it right now. So quickly flash back to Calc 1. So if you remember back in Calc 1, for a function of a single variable, we defined the increment of y as the change in y. That's basically it. So the increment of x was delta x. There's a corresponding or an associated increment in y, which is just the change in the outputs, right? And then by the definition of the derivative, you can say that the derivative at the point a is the limit as delta x goes to 0 of the difference quotient. This might look unfamiliar, but this literally is just the difference quotient that you know and love from before. Change in y over change in x, and then you let the change in x go to 0. If that limit exists, you get a derivative. That's the big idea. So What we're going to do is this. So this is the new part. We're going to denote the difference between delta y over delta x, the difference in the difference quotient, and the actual derivative by epsilon. So that epsilon is literally the difference between the approximation, the slope of the secant line, and the slope of the tangent line. That's what's going on here. So if you look at this picture over here, the pink line is the tangent line. But if we picked another point, like this one right here, right, that's the point a plus delta x, comma, f of a plus delta x. And remember here you can get a secant line, right? Maybe I'll use green. I'll start here, pass through it like that. So this green line is a secant line. And the slope of this line, slope is delta y over delta x, rise over run, delta y over delta x. So the slope of that green line is delta y over delta x. Highlight. Now the slope of the tangent line is the derivative at that point A. So the slope of the tangent line is f prime of A. And so what epsilon is doing is epsilon is giving us the difference between those two slopes. So that's what epsilon is defined as, the difference between those two slopes. Now, if we massage this equation a little bit, we can rewrite it so that we can write the change in y, the increment in y, in this form. So f prime a times delta x plus epsilon times delta x. Basically just multiply both sides by delta x and move delta y to one side, and that's how you get this. All right, so now what we're going to do is we're going to define epsilon to be equal to 0 when delta x is equal to 0. And that actually makes epsilon a continuous function of delta x. So this is what epsilon is defined as. It's the difference between the slope of the secant line and the slope of the tangent line, as long as the increment is not 0. And when the increment is 0, we just define that difference to be 0. And this is a function that is continuous. That's the idea. It's a continuous function of delta x. That's the idea. This is a continuous function. All right. So this gives us what I'm calling a characterization of a differentiable function. And this is what you can take as a definition. So a characterization is usually an alternative definition. So this is what we're saying. If f is a differentiable function, then that means that we can write the increment of y in this form where epsilon goes to 0 as, I'm sorry, yeah, the limit epsilon goes to 0 as delta x goes to 0. So this is an equivalent definition of differentiability, all right? Okay, this is one of those times where I want to throw up the thinker and I want you to just ponder this for a minute. Maybe go back a slide, maybe you should go back to here. Ponder this for a minute, think about what it's saying. It's technical, right? It's technical. You'll see why we need it in a minute here and again in the next section. All right, so now that we've kind of saw what happened with Calc 1, or back with a single variable function, I should say, now we need to generalize it to two variables. So here we go. Consider a function f of xy of two variables, and suppose x changes from a to a plus delta x, and y changes from b to b plus delta y. Then the corresponding increment in z is this. So it's the change in the outputs still. Just like it was before for a single variable function, it's the change in the outputs, right? Let me zoom in. Okay. So here's our surface. Here's the tangent plane. Here's the increment in z. Here's the increment in y. Here's the increment in x. So you can kind of see the similarity, right? That's the idea. So what is the change in z? It's literally the difference between the outputs. This is the point a comma b comma f of a, b. This is the point, well, this. I'll just say that. All right, so that's the idea that's going on here. We'll talk about dz in just a minute. Dz is basically the change in the tangent plane. We'll talk about that when we get to differentials. I do believe I have the picture again there too. Yeah, that's right. Okay. So moving forward, here is the characterization of a differentiable function of two variables. Uh, Again, this can extend to any number of dimensions, but we won't go there. This is already technical enough. I don't think, wait, do I? At the end? Give me a moment here. Do I at the end? I do. I do at the end. So we'll save it until the end. Um, we'll save it to the end. Let's move forward with this. Okay, so here we go. We say that f is a differentiable function if the increment of z can be written in this form, where epsilon 1 and epsilon 2 go to 0 as delta x and delta y go to 0. So epsilon is still defined in the way that it was before. It's basically looking at the difference in the secant plane and the tangent plane. And we can make it a continuous function of delta x or delta y. And this is how we define a differentiable function. Now, if all of this is already getting overwhelming, because it's pretty overwhelming, just remember intuitively all we are saying is that a function is differentiable if the tangent plane is a good approximation of the surface when when xy is near that point. Okay, that's the idea. So for example, on that example here, this surface right here, there it is. What I'm saying is that the function's not differentiable at the origin. That's what I'm saying. And it makes sense. It makes sense it's not differentiable at the origin. It kind of like jibes with what we would expect. Differentiability really means looks like a flat surface at that point. Notice that if you go anywhere else on the surface, like here, it is differentiable. It is differentiable. It is differentiable. The only issue is right at the origin when things get really funky. All right. So here is the theorem. um, And this, again, is kind of something we've seen already. If the partial derivatives of fx and fy exist near the point, and they are continuous, then f is differentiable at that point. So that's a powerful result because you can compute the partial derivatives, see if they're continuous, and if they are, you know that your function is differentiable there. So that continuity is baked into that characterization of differentiability. Um, we are not going to prove this. The proof is actually quite technical. So if you're a math major, I encourage you to read it on your own time. How do you prove it? You assume these are continuous. You use the characterization of a differentiable function that we just defined, and you prove it in that way. You can actually find the proof in Appendix F. So if you want to see the technical details, I encourage you to read it in Appendix F. We're not going to do it here, though, because it's just too much. All right. So this is one I want you to actually try on your own. So enough of me talking. I want you to try this on your own. So I want you to show that this function is differentiable at 1, 0, and I want you to find its linearization there, its tangent plane approximation. Then what I want you to do is use that linearization to approximate this output value. All right? So think about it for a moment. Now, say something out loud about how you will start. Remember, you can say it to anybody, your dog, your cat, your hand, the wall, just something out loud to give your brain that feedback. Okay, and now work it out, all right? Compute the partial derivatives and go from there. All right, here we go. All right, so how do we show it's differentiable? Well, this is where that previous theorem comes into play. So if these exist and they're continuous, our function's differentiable. So the first thing we should do is try to compute some partials. Here we go. Partial derivatives are this and this, just using the techniques we learned in the last section. Now we're going to evaluate them at the given point, 1, 0. So we get 1, 1. By the previous theorem, we know that f is differentiable. So now we can compute its tangent plane approximation at this point. We're going to use that formula that we had for the linearization, function value at the point, partial with respect to x at the point, x minus 1, partial with respect to y at the point, y minus 0. Then we do some simplification and we get this linearization right here. All right, so what I'm saying, do I say that right here? Yeah, what I'm saying is that this function that we're given is approximately equal to this linear function as long as we're near 1 comma 0. If we start to move away from 1 comma 0, our approximation is going to get bad. It's going to get really bad the farther away you move, in general, speaking generally. So as long as we are near this point, we could just use this linearization, and there'll be a slight error involved, but it's way easier to evaluate this than it is to evaluate this. You know what I'm saying? So this point here, the point 1.1 comma negative 0.1, is actually pretty close to this one, right? Like those are pretty close to each other. They're 1/10 away from each other in each direction. So they're relatively close. So what we're saying is that the value of our function itself is approximately the value of the linearization at that point, which gives us this. So here's x plus y. Added up, you get 1. Now, the actual value of the function, is e to the negative 0.1, which is about 0.98542. So this approximation is pretty good, right? 0.98542 is about 1. It's about 1, not too far off. It's not great, but it's all right. Maybe you could, if you recall from Calc 2, if you wanted to get a better approximation, you could do a quadratic approximation, and all of these ideas extend to those notions. But typically for polynomial approximations in several variables, that's something you talk about in a numerical analysis course. So for those that are going to take numerical analysis, you will do that in that course. All right. Okay, so now we need to pivot slightly and talk about differentials. So just like in Calc 1, you can formulate the concept of a linearization in the language of differentials. So differentials are defined like so. So if you're working with a function of a single variable, remember that dy is equal to f prime of x dx. And in this case, we're letting dx or delta x be the independent variable. I would say that the big difference between linearizations and differentials is that with linearizations, the variable involved was x. The variable involved was x if we're doing like one variable functions. With differentials, the variable involved is the difference. So it's delta x. So that's really the distinction between the linearization theory we were talking about and this differential theory we're talking about now. It's just what we're looking at, what we're basing everything off of. We can base everything off of this, or we can base everything off of this distance. That's pretty much it. Yeah, that's why we're saying that delta x is an independent variable now. So what is the big difference? So typically what I find students struggle with is the difference between delta y and dy, at least in one dimension. So let me point it out right here. So delta y is the difference in the actual function values. All right, so when you see delta y, that is the increment in your function output value. So if your function is y equals f of x, delta y is talking about the actual function itself. That's what you want to think of. Dy is not talking about the actual function itself. It's talking about the linearization. So dy is the change in the linearization, the change in the tangent line. So here to here. You see how these are, sorry, this is a different value than, oops, I'll say this is a different value than this, right? So delta y is the change in the function, dy is the change in the linearization. That is the distinction between the two, right? So if you ever forget, this picture helps a lot. Okay, now let's look at it again in 2 dimensions. So if we let dx equal delta x and dy equal delta y be independent variables, then we can define the total differential dz as this. Partial with respect to x times dx, partial with respect to y times dy. That's the idea. Oh, another quick thing. Notice here, even on this picture, for one variable, dx is equal to delta x. So this change is the same. No difference there. The difference is in the increment of the output, just like here. So just like here, again, do they say? Yeah, right here. Delta x is equal to dx. It's the increment in x. Delta y is equal to dy. It's the increment in y. But delta z and dz are not the same. Delta z is the change in the function values. Dz is the change in the tangent plane approximation values. All right. And then the total differential, there we go. The total differential dz is basically this. Notice this is similar to the formula for a tangent plane approximation. Dx is basically x minus a, and dy is y minus b, and there's those slopes. And then dz is like z minus c, or something like z minus z naught. That's kind of the idea. Kind of the idea, but remember there's a difference between delta z and dz. Okay, now let's use it. So with differentials, I find that they're easier to make sense of when you can kind of get your hands dirty. So let's do that here. Let's start with this function. If z is equal to that, we're going to find the differential dz. Then we're going to say if x changes from here to here and y changes from here to here, we're going to compare the values delta z and dz. And we'll do something similar in the activity as well. All right, so for this one, let's see. I want you to ponder this one first. So think about it for a minute. Okay, and then just say something out loud to yourself about how you would find the differential dz. Just something simple. Right. Now I want you to try to find the differential dz, and then we'll work through both of these parts together. All right, here we go. So if we want to find the total differential dz, we're going to have to compute some partials, right? So that's the first step. We're going to compute the partial with respect to x, the partial with respect to y. There we go, there we go. So dz is not too hard to write. We're just going to use that formula. And there we go. That's it. So that is dz. Now hold on to that. The beauty of dz, the beauty of the differential is that it's got linear stuff going on in this case. Like this is easier to compute than what we're going to see in just a minute. So you'll see the utility of these differentials. That's what part B is for. So x is changing from 2 to 2.05. Y is changing from 3 to 2.96. So let's put together what dy is, dx is, and so on. So let x be 2 and let dx be 0.05. It's like the difference, right? It's the difference between 2 and 2.05. That's the change in x. That's the increment in x. Let y be 3, and let dy be negative 0.04. That's the change in y. Now we can use dz, the differential, to get this value. So we plug in our numbers for x and y, plug in our numbers for dx and dy. So dx, dy, simplify, and we get 0.65. So that is dz. That is the change in the tangent plane approximation at that point. Now, compare that to the actual increment of z. So the increment of z is the literal change in the function values. So this is like you plug in the numbers to your original function, take the difference, and get a result. So here's how we do that. Evaluate f here, and you get this. Evaluate f here, and you get this. And you take the difference. Okay, here's the moral of the story. The moral of the story is notice that delta z is actually pretty close to dz, right? The difference here is that dz was way easier to compute. It was easier to compute. The functions involved, the partials involved were much easier, right? So like if you've got a polynomial function, kind of like the one we started with, and you do a derivative, you're gonna drop down a power, right? So you're decreasing the complexity of the analysis or decreasing the complexity of the problem. The only caveat is it does introduce a certain error, right? These are not exactly equal. dz was 0.65. Delta z is 0.6449. So we lost a little bit of accuracy by using this approximation, as expected. Right. Let's do another example. Here's a fun one. So the base, radius, and height of a right circular cone are measured at 10 centimeters and 25 centimeters respectively. So we got a cone, we've got, what is it, the radius is 10 centimeters and the height is 25. Here's the picture. Here we go, right circular cone, radius is 10, height is 25. That's what we're looking at. Now here's where things get interesting. So anybody that's going to go into industry, you got to think about this stuff. Um, uh, where is it? Yeah, so we measured this cone. So we measured the cone and we produced these measurements, 10 centimeters and 25 centimeters. But anytime you try to measure something in real life, there's an error involved. There's an error involved. And what we know with our equipment is, hey, we took these measurements, but the error in our measurements could be as much as zero point 0.1 centimeters or 1 millimeter. So even though I'm measuring it at 10 centimeters, I could be a millimeter off maximum. So whatever measuring instrument I'm using, like calipers or a tape measure, there's an error, right? So what I'm saying is, hey, it could be off by a millimeter. So now the question is, if we are off by a millimeter, how much will that make the volume off? So if I want to calculate the volume of the cone using these measurements, there's an associated error because each one of these measurements has an associated error. So I want to know, what is the possible error in volume if I use these measurements that you gave me to compute the volume? How far off could the volume possibly be, right? So what we're going to do is we're going to use differentials to make life a little easier. And I'm going to use differentials to estimate the maximum possible error in the calculated volume. So this one I want you to think about first. So let me do this. Think about what you would do first if you had to find, the volume or the error in the volume of the cone. Okay, now say something out loud to yourself about what is the error in the volume and what is the approximate error? And then we'll work it out together. Actually, I'll say this. Okay, here you go. So if you want to try to work it out on your own, go for it. See if you can calculate it on your own. We're going to do it together right now. Right. Okay. So here we go. You might recall that the volume of a cone is 1/3 pi r squared h. If you don't, that's okay. You don't need to have that memorized. What's nice about being in Calc 3 now is we can actually describe this as a function of two variables. We have that ability now, whereas we didn't, we couldn't do calculus in Calc 1 with two variables. Now we can. So the volume of a cone depends on two things. It depends on the radius and the height. It's a two variable function, right? So let's compute dv. So we're going to use that formula, dv. Oh, also notice the formula for these things is actually pretty intuitive because if you could cancel these, you would get the sum of the partials in v. So dv is partial v partial r times dr, partial v partial h times dh. If we compute the derivative of this with respect to r, we get this. If we compute the derivative of this with respect to h, we get this. So this is a formula for dv. Now, the moral here is we're going to use this formula for dv to estimate the actual error. So delta v is the actual difference in volume, right? But what we're going to do is we're going to use dv to estimate the actual difference in volume. So the error in this case, associated with the error in length of 0.1 centimeters. Here we go. We know that 0.1 centimeters is the largest error in length, the largest possible error. So that means that the difference in r, the delta r, is no greater than 0.1. And the difference in h, the largest error in h, is no greater than 0.1. So we're going to take dr and dh to both be equal to 0.1. Now we can use this to get an estimate on the error in volume. So the actual error in volume is approximately this, which is about 63 centimeters cubed. So that's about what the error could be. Okay. All right, actually, we're nearly done here. Yeah, this actually isn't so bad. I know this is already a lot of stuff, so your brain's probably cooked. But just to top it off, a little cherry on top is extensions to functions of several variables. So naturally, we can extend all of these ideas to higher dimensions and multivariable functions. We don't have to stop at 2. We don't have to stop at 3. But how you would generalize it really is just doing the same thing we did, I mean, this way, the same thing we just did a minute ago, except now you got more variables. So in general, a linearization of a multivariable function at a given point is what we call a tangent hyperplane approximation, a tangent hyperplane. Um, so maybe if you think of like a line in 1 dimension and a plane in 2 dimensions, in 3 dimensions you would have a what we call a hyperplane, but it's kind of like a hypercube. It's like a hypercube in some sense. And what is this tangent hyperplane approximation? It's the hyperplane that best approximates a function at a given point. That's it. So here is the definition of a first order approximation in Rn, a function of n variables. And for ease, we are going to use the vector notation for our point, just to keep the formulas concise. So let f be a function of n variables that has continuous partial derivatives at the terminal point of our vector a. So that's like the point where we're performing the linearization. Then the linear function L sub f of x, whose graph is the tangent hyperplane at that point, is called the linear or hyperplane approximation of f, and this is its equation in general. There it is. So it's very, very similar to what we saw before. Let me actually flash back. I'll show you. So that's 42. So let me go back to this for a minute. Compare these. Not that. Where are you? Where are you? Right here. Yeah, there we are. So take a look at it, what it looked like for 2 variables. It was like, okay, evaluate the function at the point, partial with respect to x at the point, x minus a, partial with respect to y at the point, y minus b. If you had to extend that to, let's say, 3 variables, you can probably guess at what it would be. Evaluate the function at that 3 coordinate point, partial with respect to x, partial with respect to y, partial with respect to z. That's exactly what it is. So now compare that to this generalized formula right here, and you'll see that it's kind of the same structure. This is the partial with respect to the ith coordinate evaluated at the point, and then this is the difference. So x sub I minus a sub I. Wait, should that be x sub I? Yes, yeah, it should be x sub I. Yeah, it should be x sub I because these are our coordinates now. That's the thing. When you get into higher dimensions, you can't use x, y, z anymore. You need a more generalized version. So that's what that is. Same theory as before. Our function is about equal to that linearization as long as we are near that point, and the increment is the change in the output. It's still the change in the output again. That's pretty much it. So here's what it looks like for 3 dimensions. So let's say if you've got a function f of x, y, z, it's a function of 3 variables. Let's say it's got continuous partial derivatives, fx, fy, fz, at that point a, b, c. Then the linearization is this. This is exactly like what I'm sure some of you were thinking when I mentioned it just a minute ago. Yeah, it's pretty much what you would expect. That's the best part. And the increment too. The increment too. All right, now on that note, let's play. So this is something that we'll explore during the activity. I know it's a lot of stuff, so as always, thank you for bearing with it. I know some of these can get a little bit long. I'll try to talk faster, I suppose. But on that note, I will see you next time, and thank you for watching.